Hello everyone, my name is Tanya Garg and today we will be talking about convolution. So, what is convolution? Convolution is basically a mathematical operation that we apply on two input signals. These two input signals give us a third output signal, which is basically a representation of how one input signal is modified by the other when the two are combined together. The output of convolution can be calculated by integrating the product of the two signals after one of the signals has undergone time shifting and time reversal. Time shifting is basically shifting the signal with respect to time by a period of time, say t naught. And time reversal is a kind of time scaling where we scale the time parameter of the signal by a constant a or a function of t, say t square. So we have two types of signals, continuous signals and discrete signals. The convolution operator works for both of them. Here the asterisk sign that we can see is the symbol of convolution. So in the continuous domain, convolution is represented as x1 convolution x2, which is equals to yt is equal to integration from minus infinity to infinity x1k into x2 t minus k dk. Over here we can see that we're integrating with respect to a separate variable k, thus our signals have undergone variable change. We can see that the second signal has undergone time shifting as there's another parameter t over here, and it has also undergone time reversal as over here we have k while in the second function we have minus k. Similarly, in discrete signals, we have x1 convolution x2, which is equals to yt, which is equal to summation from m equals to minus infinity to infinity x1m into x2 t minus m. Now the question arises that why do we use convolution in signal and systems? In signal and systems, we have a very important category of systems known as the linear time invariant or the LTI systems. These systems are important because the output of these systems can be easily analyzed by breaking the input signal into various signals because the system itself is linear, that is, it satisfies the properties of superposition, and it is time invariant, that is, if we shift the input by an amount t naught, then the output signal is also shifted by the same amount. Then we have the impulse response ht, which is the output of the LTI system when the input is a unit impulse signal. A unit impulse signal is a signal at the origin with width of 0 and a height of infinity with an area of 1. Therefore, if the input to an LTI system is a unit impulse signal, then the output is the impulse response, which is ht. So, where does convolution come into play over here? Convolution can be used to find the output of any signal xt when it is fed to the LTI system. The output is nothing but the convolution of our input signal xt with the impulse response ht. Therefore, we can see that the output can be easily calculated if we know ht, which is the impulse response, which is a characteristic of the system. Now we will discuss how the result of convolution is calculated. Suppose we have two signals, a square wave signal and a triangular wave signal. The first step is variable change. Here we change our variable from t to k. Therefore, our first signal becomes x1k and the second signal becomes x2k. The second step is time reversal of x2k. The first signal remains as it is, while the second signal undergoes time reversal. Time reversal is basically taking the mirror image of the signal with respect to the y-axis. Therefore, a signal x2k becomes x2 minus k. The third step is time shifting. The first signal remains as it is, while the second signal is shifted by a parameter of n from the origin. Therefore, our signal becomes x2 n minus k from x2 minus k. Now what happens is the first signal remains in its own position as a constant value, while the second signal is shifted over the first signal from all the values of k from minus infinity to plus infinity. As we can see over here, the square wave signal remains in its place, while the triangular wave signal is being shifted from minus infinity to plus infinity. As the overlap starts to begin, the value of the convoluted function also increases, as convolution is nothing but the overlapped area of the two signals. As there is complete overlap between the two signals, we get a maximum constant value of the convoluted function. As the area starts to decrease, the convoluted function also starts to decrease till there is no overlap between the two signals. When there is no overlap between two signals, we get a zero value for the convoluted function. This is the MATLAB code that was written to create the previous output. T is the time period for which we want to calculate our convoluted function. These are some elementary signals that were used to create the square wave and the triangular wave function. This part is the main part where we calculate the convoluted function. Over here we can see that the convolution is nothing but the area of overlap. We're actually adding the multiplication to the convolution at a particular point. Therefore, convolution is not the multiplication of two signals but is the area of overlap. Over here we can see that we have displayed our two signals. This is to display our two input signals, while this part is to display our output signal, which is the convoluted function. We will now discuss some properties of convolution. Convolution is a mathematical operator which satisfies the commutative, associative, and the distributive property. To find the differentiation of convolution of two signals, we can simply differentiate the first signal and convolute it with the second signal, or we can convolute the first signal with the differentiation of the second signal. For finding the integration of the convolution of two signals, we can similarly integrate the first signal convoluted with the second signal, or we can integrate the second signal convoluted with the first signal. Multiplicative identity. Multiplicative identity is that signal which gives us our original signal back when it is convoluted with our signal. Over here, if we have a signal, say ft, and if we convolute it with a signal, the unit impulse signal, then we get our original signal back. Therefore, the unit impulse signal is the multiplicative identity of convolution. The convolution theorem. The convolutional theorem states that the Fourier transform of convolution of two signals is equal to the product of the Fourier transforms of the individual functions. Fourier transform is used to convert the time domain to the frequency domain. We use this because it makes the analysis of various circuits quite easy for us. We can see that the Fourier transform of the convolution of two signals f and g is equal to the Fourier transform of f into the Fourier transform of g. Therefore, from this equation, we can see that convolution in one domain, that is the time domain, is equal to the multiplication in another domain, which is the frequency domain. Now we will discuss some applications of convolution. Image processing. Convolution can be used to filter the components or some features of an image by using a kernel. A kernel is nothing but a matrix that is convoluted with the pixels of the image to get a brighter, finer, or a different kind of image. Over here, we can see that in our kernel, there's only one in our 2,2 element space. Therefore, when we convolute this particular kernel with the pixels of our image, we get a sharper image. In this example, we can see that there are negative values at the corners of our kernel, thus we get a negative form of our original image. Convolutional neural networks. These neural networks are inspired by the neurons present in our brain. These help to extract features from an image and it gives out the particular feature of the image. Over here we can see that we have an image of a car. We take a particular section of the image and put it in the convolutional layer. This convolutional layer extracts some features of the image and send it to the pooling layer. This process continues till we're able to distinguish if the original image was of a car, truck, or a bicycle. Sound processing. Sound is a signal which is of mechanical nature. By converging two types of sound signals, we can get a sharper sound, an echo sound, or even a different sound note. Let's see how we can convolute two sound signals by using MATLAB. Here we have two audio files, audio file 1 and audio file 2. These files can be easily downloaded from the internet. Here we're using the audio read function, which is an inbuilt function of MATLAB, which gives the frequency and the array output of our original sound signal. Similarly, we take out the array output of the second audio file too. Here we are convoluting the first two audio files. We use the similar function that we used in our previous example where we convoluted the square wave and the triangular wave signal to convolute our two sound signals. Now let's hear our three sound signals. This is our first audio file.
Nice work.
This is our second audio file. As we can see over here that it's an impulse function which goes on for a long time, therefore it is an echo signal. This is our convoluted audio.
Nice work.
Here we can see that in this convoluted audio, our first two audio files were combined and there is an echo that is present in our first audio file. Thank you.